Good afternoon. Welcome to today's Liftoff webinar. We are the National Advanced Materials and Manufacturing Innovation Institute. At LIFT, we are advancing American manufacturing through technology innovation and talent development with the core mission ensuring building of advanced materials and processes that support our nation's economy and security. As the public-private partnership, we focus on strengthening the defense industrial base, connecting and convening government, industry, and academia to accelerate the transition of advanced materials, manufacturing processes, and systems engineering. My name is Christine Longroy. Thank you for joining us today. I'm the Vice President of Business Development here at LIFT, and I'm excited to welcome you for our today's webinar. And I'd like to welcome Ellen Williams, the Executive Vice President of Business Development at Exum, who's going to be talking about insights on chemistry at the point of need, where it's a critical area of focus as we work together to close the materials gap in the manufacturing sector. Ellen is an atypical engineer who combines her highly technical background with business acumen and strong communication skills. So Ellen, welcome today's and look forward to hearing this very important topic. So take it away.
Great. Well, thank you so much. I am pleased to be here and really appreciate the opportunity to speak to the LIFT community about something that's very important to us, which is measuring the chemistry of materials. Because at Exum, our mission is to redefine the possibilities of analytical chemistry and make it easier to measure and gather the critical chemistry data that we need as part of our advanced manufacturing and defense industries. So just a quick agenda here. I'm going to start just to make sure we're all on the same page about the importance of chemistry for these industries that we focus on. I will then go through the fundamentals of our technology. Commercially, our instrument is called the Massbox, and you can see it sitting in LIFT's Metrology lab in the picture on the right there. The technique behind it is LALI TOF-MS, which I will go through in more detail. And then I will go through 3 different applications for advanced manufacturing and defense. That includes a powder example, as well as a functionally graded material, or FGM example, and a defect analysis example. And then, of course, summarize and take your questions. So please feel free to put the questions into the question and answer session as they come up. But I do just want to remind everyone that our technology sits in LIFT's Metrology lab. You can see it there behind our CEO and CTO, Jeff Williams. This was actually the last time we presented a LIFT webinar, and it was right after we had delivered the Massbox to LIFT's facility. You can see John Keogh there, very excited because he actually has a background in analytical chemistry and recognizes the challenge of traditional mass spectrometry and spectroscopy techniques that we have overcome with this technology. So just setting the stage here of why we test chemistry. I'm sure a lot of you are familiar with this, or you wouldn't have chosen to attend or to watch this. But anytime we're developing new advanced materials, we want to experimentally validate that what we have designed meets what we were intending to design. And then, of course, when it comes to even just common metal alloys, we need to make sure that those elements are within those specified ranges in order for the metal to have, metal or ceramic, I should say, or any material to have the performance and mechanical properties that we expect it to. And that can be especially important when we think about recycling materials and making sure that we're not picking up additional oxygen or nitrogen or any other potential impurities or contaminants. And then a big way that chemistry can help us is answering questions like, what is it and where did it come from? Often chemistry can help us pinpoint the source of a contaminant or where a supplier is getting their materials. If we have an inclusion in a material, then chemistry can help us determine how it formed. And of course, there's often a chemical reason for failures. And then we're going to go through some examples today on multi-material interfaces, which are especially critical to understand the chemistry. So despite the importance of chemistry, it can be a bit challenging and require multiple different analytical equipment in order to get a good sense of the chemistry of your materials, especially solid materials. So when we look at kind of these two ends of the spectrum, where we've got really the gold standard when it comes to trace quantitative information with the ICP, either optical emission spectroscopy or mass spectrometry, those sorts of techniques are excellent at getting down to even parts per billion, in some cases can even be parts per trillion level of accurately quantified elements of a material. The challenge is that you have to digest your solid material in acid in order to get it into a liquid form in order to use those techniques. So you get no understanding of how those elements may be distributed. On the opposite side of the spectrum, we have something like a scanning electron microscope with energy dispersive spectroscopy that can be excellent at getting very sensitive elemental maps, and by sensitive I mean spatial resolution wise, down to nanometer level resolution, but lacks the sensitivity in terms of trace elements. So you're typically limited to things in the weight percent, potentially high thousands of parts per million. And so really our technology, the LALI TOF-MS, which is embodied by the Massbox, fits in between these two different solutions and fills this gap. We're able, because this is a mass spectrometry technique, we are able to measure trace elements down to the sub parts per million level, while at the same time creating elemental maps to show how elements change spatially down to micron level resolutions. So really complementary to those two pieces of equipment that you're likely already using or use external labs to use. So what this is, I'm going to go through this acronym in a little bit more detail of how it works. The laser ablation, laser ionization, or LALI part is what is unique to our technology. It's something that we have developed and patented. And really the driver behind this was to make it easier to get mass spec level, high sensitivity data on solid materials without having to go through the full a full lab's worth of digestion equipment and ancillary equipment to get all of the elements of the periodic table. So you can see that the system just sits on a desktop. If you've seen it at lift, you see the small footprint that it takes up with just a single power cable, and then we can just directly analyze any powder or solid material. So the way this works, we have that laser ablation step that comes in. We have that first laser that hits the sample perpendicular to it and ablates or removes on the order of tens to hundreds of nanometers per laser pulse. This is done in a vacuum environment, so we're able to measure some of the interstitial elements like carbon, nitrogen, and oxygen that are traditionally very challenging. Being in a vacuum environment also means that we can analyze things that may be air or moisture sensitive. Once we have that ablated plume of particles, we then use a secondary laser to create ions. Every mass spec technique needs ions. The way that we're doing it here with laser ionization, we're essentially just stripping off an electron from the neutral particles, meaning we're not creating ions from a plasma like the ICP techniques. That P stands for plasma. We're not using any sort of argon gases or other gases that can create interferences. The result is that once we get our ions, then it's very easy for our software to act as the analytical chemist and isotopically verify all of the elements that you have in your material. Once we have all those ions, we hit them all with the same amount of force and send them to our time of flight mass analyzer. What this does is it measures the difference in times that it takes for ions of different masses to impact that detector. The advantage here is that we get a full mass spectrum, everything from lithium to uranium, at every single one of those laser spots. That means we don't need to be looking or tuning for certain materials. it allows us to very quickly screen an unknown material and see the elemental signature and know exactly what it is. We can also verify that any sort of contaminants may not be in our material without necessarily having to look for it. So it can be really helpful when it comes to that what is it, where did it come from question. So what this allows us to do is three unique things, again, all combined in a single desktop package. As I mentioned, mass spectrometry is the gold standard when it comes to quantitative compositional analysis. So we can do that as well. This image that you're seeing here is a graphical representation of the technique's detection limits, where the darker blues are down to the sub parts per million level, and even these lighter blues are in the parts per million range for some of these low mass elements that can be traditionally very challenging to measure with X-ray or other spectroscopy techniques. So you can see every element that is colored there we can detect, and the different colors represent a range of detection limits from sub parts per million to low parts per million. As I alluded to, because this is a laser-based technique, we can also see how those elements vary spatially. We can create elemental maps on a millimeter scale with micron level resolution. The resolution of a map is defined by the laser spot size, and the user can adjust that from 5 to 150 microns, allowing us to get a range of different quite a versatile mapping capabilities, and we're going to show a few examples of that going forward, of being able to do broad scale coarse maps combined with high resolution smaller maps. And then because we're actually ablating or removing material, we can create a three-dimensional depth profile by repeating that elemental mapping process layer by layer, removing material. There's again a lot of versatility on the resolution of the depth profiles as well, because the user can change the laser power to either remove more or less material. So if you blast it with a lot of power, we can remove up to microns of material per layer, or if we dial the power back, then we can remove as little as tens of nanometers per layer to create depth profiles of different resolutions depending on the application. So now that I've given you an overview of the capabilities, I'm going to go through three application examples that show each of those modalities. And the first one I'm going to start with is for powder quality control, where we worked with LIFT to develop a proof of concept method for testing the multi-element composition of a Ti-6-4 powder. And the reason why we were inspired to work to develop a method like this is because you may be familiar with the fact that it takes multiple standards and multiple different techniques in order to get a full compositional analysis of really any powder. But for titanium powder, let's just look at some of the standards that you might use in order to test the elemental composition. So you may start with the first standard there. You may have WD-XRF, and that does give you a range of metallic elements by following that standard. But for particular industries or applications, there may be other trace elements that are below the detection limit of XRF. And so you may have to use the second standard, which is that ICP, optical emission spectroscopy technique that I mentioned earlier. So then you're dissolving the powder into acid to do your ICP to get some of these other trace elements, maybe boron, maybe tungsten. But then neither of these techniques give you a sense of how much oxygen or nitrogen is in your powder, which would be important if we were doing recycled powder, or if we need to verify that our oxygen is not exceeding the specified limits for Ti-6-4. So then we're using that third test method and technique of inert gas fusion to get our oxygen and nitrogen, and then a fourth if your specific industry requirement needs you to verify carbon as well. So 4 different standards, 4 different analytical techniques in order to get all of the elements that you just saw on the previous slide, Massbox is capable of measuring. So now to develop our own methods, test methods for verifying the chemical composition of a powder, we first need a calibrant, a certified reference material. There are several of these available commercially, and so this one that you see on the right here is one that has been developed by a standards company, has gone through a rigorous testing process, includes, uncertainty ranges for all of the elements, and we have a lot of confidence in the accuracy of these elements. So this is an excellent material to use as a calibrant, but then we also need a second material that can be used as a reference so that we can verify that the method that we're getting is giving us accurate results. So in this case, we have what you see on the left, which is a Ti-64 reference material we received by a customer that had sent this out to one lab and gotten one number for the elements of interest that you see here. So it's important to point out that for this method scope, we are limited to the elements that have been quantified in our reference material. Again, Massbox can detect and quantify all of the elements that you see on the right in the certified reference material, but without a second material to verify that we're getting those answers right, then this current proof of concept method was limited to the elements that you see here. It's also ideal that those elements are within a similar concentration, so plus or minus 20%. And so you can see in this particular case, the major elements, Ti, aluminum, vanadium, as well as a couple of minor elements, iron and oxygen, meet those criteria. So those are the elements that we included in this proof of concept method. Again, if we had more reference materials with closer values to those of the CRM, if we had reference materials with more elements quantified in them, we can expand this method scope. But what we did was use these two samples, and we did an optimization process of sample prep. So how we pelletized the powders into these little pucks that you can see here. It's a pretty straightforward process. It's just a matter of applying a bit of hydraulic pressure so that we aren't, putting a chamber full of powder into our instrument with the lasers. We essentially just have to adhere them to something. And then we experimented with different laser powers as well as analyses areas. We also will typically do a cleaning run where we do a first layer pass of ablating the surface layer, removing that from the quantitative results, and then average across several areas below that cleaning run. So that's what you can see there on the analysis area. All of this process, this method, took about 15 minutes per sample. So again, much easier than digesting your powder and acid for ICP techniques, and again, able to get those metallic and oxygen numbers in the same analytical session with the same technique. So what you see here is once we developed that method, we then repeated the same method 36 times over multiple months, over multiple instruments and multiple users in order to get the Y square data blocks that you see on that graph. So we're first just looking at titanium while I orient you on the data that we're presenting here on the results. You can see all of those measurements from 1 to 36 shown in blue, the average of all of those measurements shown in red compared to the target number based on the known results from that reference material that we had. We also statistically determined the measurement uncertainty, which is what you see as those gray bands there, just based on the variance that we saw in the measurements. So you can see that we have reliably quantified all of the elements that were included in this particular proof of concept method: Ti, aluminum, vanadium, iron, and oxygen. We can see that those average results that we're getting are quite close to that of the target. Again, to make those a little bit closer, we could get some more confidence in the numbers, the target numbers that we have, so that we're not just using a reference material that has only been analyzed once. We could get more data points to have more confidence in that target number. The other thing that I want to point out is that The remaining the last six data points that we acquired here were what we did at LIFT as part of a gap validation study, where essentially we developed the method in our own facility in Denver, Colorado. We then brought the method steps to the LIFT Massbox and said, let's do the same method here, verify that we get the same results, and you can see that we did for all elements. All of those elements landed within that measurement uncertainty range, giving us the confidence that this method can be applied to multiple mass boxes and can be repeated by multiple users. So again, certainly more to be done in terms of developing methods that include a greater number of elements. We're also working on different material types, but essentially we developed the blueprint that we can now follow for other materials and to just continue gathering up the data that would be required to get this to be a true standard test method. So the next application example that I'll go through is for process control, where we're looking at some elemental mapping of omnidirectional functionally graded materials. So you may be familiar with this term, functionally graded materials. I know this is a pretty hot topic in advanced manufacturing and defense because it allows us to spatially tailor the chemistry and the properties of a given part so that things can be strong or heat resistant where they need to be, but light and inexpensive in another area of the part that maybe doesn't need the same mechanical properties. And so these have been around for a little while, and actually the next example that I'm going to show you is one where we have a discrete change between two materials. They're typically done by directed energy deposit, or DED, and in the past, it's relatively straightforward to change powder types between layers, right? So, I'm printing with a stainless steel, now I switch to an Inconel, but omnidirectional functional graded materials where we actually change mid-layer has traditionally been fairly difficult to do because of that interlayer material change. You may be familiar with a company called Formalloy that has developed some pretty innovative technology that allows these omnidirectional functionally graded materials, or as the Department of War calls it, the materials on a continuum. So what you're looking at on the bottom here is a diagram of one of these omnidirectional functionally graded materials, where you see we've got a steel substrate and then the printed stainless steel 316L transitioning to Inconel 625 at a 45-degree angle over an 8mm range. So, pretty impactful that they're able to create their technology that allows them to do that material change, as well as, some innovative kind of powder feeding mechanisms that allows this to occur. So what we did was we took a cross section of the diagram that you see there. What you're looking at an image there in the top right, and I do just want to point out that you probably see some porosity here, and so the parameters for this particular study are not optimized, and they certainly can be improved in order to improve some of the porosity that you see here. But still a pretty, again, just going back to the fact that omnidirectional functionally graded materials are not very commonly done, and so it's still pretty impressive that Formalloy's technology can do this this transition in the XZ direction from a steel alloy to an Inconel 625. And so what we did was we did an elemental map across this cross section in order to see those compositional changes. So you can see the microscope image there on the bottom right that will then look at the elemental changes across this area. So what you're seeing here is one of our elemental maps. In this case, we're looking at iron. And for each elemental map, they'll be on their own relative scale, where the warmer colors, the reds, the oranges, those are relatively high concentrations of a given element compared to the darker colors, darker blues that are relatively low amounts of iron. And so you can see in this case, We've got the highest concentration of iron is where we hit just a little bit of that substrate, and then we see a relatively high concentration of iron in the bottom left corner, transitioning to a lower concentration up in the top right. And that makes sense. We know that iron is a major constituent of 316L stainless steel, and it's a minor or lower concentration in the Inconel. Every single one of these pixels that you see on one of these images is a 100 micron laser spot with a full mass spectrum of data behind it. So then we can look at all of the other elements of interest that we measured here. So chromium, for example, is relatively higher in the 316 and then transitions to a relatively lower in the 625, but there's still quite a bit of chromium in the Inconel 625 as well. So we see high levels of chromium up in the top right of the analysis. Of course, nickel, we see the opposite trend as we do the iron, because nickel is the primary constituent of the Inconel 625. And then we see molybdenum mirroring the nickel pattern as well, since it is more present in the Inconel than in the 316. So again, room for improvement in terms of the porosity and optimizing the parameters, but an excellent proof of concept to show that Massbox's broad scale elemental mapping, we're looking at a 35 millimeter by 25 millimeter area here that was done in about an hour, can be very useful when it comes to process control and developing new advanced manufacturing techniques and new advanced materials, especially where we have a chemical gradient. The next step of the study with Formaloy is we will be actually quantifying the composition along this line. So again, going back to the first modality of being able to provide quantitative data as a complement to the elemental mapping and visualizing the elemental changes across this area. And so then the final application example that I'll go through is a defect analysis, where I'll just kind of walk you through our typical process for analyzing and characterizing and diagnosing defects. So this is once again another functionally graded material. We're looking specifically at a multi-material interface. In this case, we're not looking at a gradient. Essentially, we're looking at just a discrete material change. This was a collaboration with Ohio State, where what they have done is strengthened the notch of a tensile bar with an Inconel 718 and then use stainless steel 316L in the tensile bar's grips in order to use an alloy that has preferred mechanical properties for the area where you need the tensile bar to be strong. But of course, anytime that we are changing material types, and when we're going through this printing process of changing material between a layer, we are going to have differences in mechanical properties and potentially some defects or weaknesses at that interface. So it's really important to understand what sort of compositional gradient we're getting right at that interface, and determine how we might want to improve that going forward. So what a typical workflow looks like for us when we're looking for defects, looking for contaminants, is we'll do a relatively large scan with a relatively large spot size in order to find the area of interest. In this case, what we're looking for is exactly where that Inconel to stainless steel transition happened. So you can see we did this 25 millimeter long area across where we anticipated the material change to be, and then looked at the elemental maps here, again with a 100 micron resolution, so a relatively coarse resolution. We're looking at two maps side by side, again with the same color scale, where we see that relatively high concentration of iron compared to a low concentration of nickel, and then vice versa on the other side, we found that interface. We know that we see the nickel alloy on the bottom, and that has transitioned to the stainless steel on the top. So then that allows us to do smaller areas with much higher resolution really investigate that interface that we were looking for in this study. So here we're looking at this smaller area with a 30 micron laser spot size, so giving us a higher resolution look at these really 3 distinct areas that we see here. So of course, where the iron is low, that's our Inconel 718. Where the iron is high, that's our 316L. But then we've also got this area where iron is moderate or medium, and that's our interface. And so what you see here is the size and shape matches the melt pool beads that were created as part of this DED printing process. And if you're not familiar with the DED process, you can see that in the diagram on the right here, where we have, you know, those melt pools with a essentially a diameter and a size and shape consistent with the pulsed laser diameter. Because as we're creating a plasma, heating up the powder and melting it, we get this phenomenon that you see in the bottom here of this melt pool, that you can see this curved shape that we're identifying in the map, and then this Marangoni flow as well. And that's actually what we're able to see here, where we have those areas with relatively low iron. That is that Marangoni flow mixing, where we're getting some of that segregated nickel alloy within the iron as it's being deposited on the next layer. So really important defect to identify and to characterize and determine, are there some processes, are there some parameters that we could potentially change in order to minimize how many defects and impact the compositional gradient zone that we see here, in order to make sure that we don't create any sort of weak points at this multi-material interface. So the next slide here, I'll just show you what some of the other elements look like here. So again, we've got our iron map, and then the same area, we're looking at the nickel, where you see a much less of a stark gradient, because again, nickel is the bottom layer, and then as the iron is, or sorry, as the steel is solidifying above it, then we get less of a stark gradient in that melt pool. But you know, those areas where we see low iron is exactly where we're seeing some of those, you know, yellow and green on the nickel map, where we're getting some of that nickel alloy mixing into the iron melt pool. We can also point out something like molybdenum, which has a very similar composition within both of these alloys, and we can see there's hardly a gradient across these two materials, because it's in around the 2 to 3 weight % in both materials. We see a fairly uniform composition of molybdenum across the same area. Manganese is a minor element. It's less than 1 weight % in the 316L, and so you can see that it follows the same pattern as what we see on the iron, since it's primarily only in the 316L and not in the nickel alloy. The other thing that the researchers noticed from these results were these horizontal bands that you can see occurring once we've transitioned. You can even see it on the nickel alloy side as well, that they interpret as being some dendritic features that are occurring in this printing process. So again, certainly there's plenty of characterization going on here that can then inform the next iteration of these builds and inform the process improvements to minimize how many defects we may potentially have. And then the final piece that I want to show here is an example of our depth profiles. So in this case, we've analyzed the other side of the tensile bar, where you can see the steel on the left and the nickel on the right. Again, we're looking at an area where we're able to see that curvature representing that melt pool mixing, and consistent with the size and the shape of the DED laser. What we did was we analyzed a 3.5 millimeter by 3.5 millimeter area. We repeated that for multiple layers until we got through about 10 microns of material. And then we're visualizing how the iron and nickel concentrations change in 3 dimensions. So once again, we can see kind of those defects created by the Marangoni flow that are sort of, going around that melt pool, that curved area. And we can just kind of see how that changes from the surface layer to below the surface. So again, a really, really impactful modality and ability to see not just how elements change in the XY direction, but also how they change in depth. And I think I'll just let this video play once more, just so you can see that once again, now that I've oriented you on the map. Doing that map, identifying where that interface layer is, and then doing a smaller area of 3.5 by 3.5, profiling through tens of microns of material. And of course, if we continued that process for a few more hours, then we could even get through a deeper amount of material. I believe the deepest depth profiles that we've done to date have been about 350 microns of material removed in order to see a specific feature and how that changes over hundreds of microns of material. And I also want to remind you that we're just looking at iron and nickel here, but we're also easily able to look at all of the other alloying elements and see how those change in this melt pool and how that compositional gradient zone has different alloys that are behaving differently. Sorry, different elements behaving within those 2 alloys. So finally, just want to summarize that I hope you have seen from these application examples how the Massbox, how our technology addresses the critical needs in materials characterization by combining these 3 unique things into a single package that's relatively easy to use for solid materials. The fact that we don't have to digest things in acid, we can just directly put in any large solid or powdered material and get full quantification as well as elemental mapping or depth profiling to see how elements vary with depth. That quantification can be done from trace levels in the subparts per million all the way up to weight %, and even includes things like carbon, nitrogen, and oxygen that are traditionally challenging with other X-ray or spectroscopy techniques. This allows us to deliver solutions across advanced manufacturing and defense, specifically when it comes to additive manufacturing. I know I covered a lot of additive manufacturing examples here, but I know that is something that the audience cares quite a lot about, especially when it comes to powder analysis, how complicated that can be to get all of those elements of interest with all of those different techniques. We can simplify that process quite a bit. But what you saw here were examples of metals, but we can analyze anything solid, and we have a lot of experience analyzing ceramics as well as polymers and geosamples. If there's anyone in the audience who does anything with rocks or geologic samples, and we've even analyzed a matchstick to demonstrate that this process can be done on energetic materials without igniting any issue. So lots of different materials kind of across the board. And we also walked through how you could use this for process control to verify that what you're creating matches what you intended to create, what you designed. And then an example of how we would go through a defect analysis or potentially a failure analysis, where we can scan a large area, then identify an area of interest, use a smaller laser spot size, and get a really high resolution view of the defect or failure of interest. And then we can even do a depth profile to see how that failure penetrates subsurface. So with that, I am looking forward to taking your questions. And if I don't get a chance to answer your question, then you are welcome to reach out to me. I have my email address there. But yeah, appreciate it. Thank you so much for your time. Yeah, go ahead.
Thank you. I appreciate it. Very detailed importance of why gathering this critical data is really important. And as you just said, how you talked a lot about additive, but additive is being addressed, and the fact that you have all these critical skills and the capabilities is super important. So let's get to some questions that have come in, and the fact that you can not only address other materials like the ceramics and the polymers and the geological things, as you just explained too. So that's super valuable for the industry. So let's get addressing a couple of questions. What sample preparation is required for a Massbox? So take it away.
Absolutely. So I do want to show, one slide, I guess, just that I didn't go through in the presentation, just to again reiterate the versatility of the Massbox and its ability to analyze any solid material. So, for example, the tensile bars that we analyzed, as well as the functionally graded material, anything solid like that, we just essentially just put it into our sample tray, adhere it with some vacuum compatible tape like a copper tape, and we can just directly analyze anything solid like that. For powders, you can see we have some examples here where we're pressing them into a pelletized puck and just applying a little bit of hydraulic pressure. If you want a really quick analysis and don't even want to spend, the few minutes putting it into a hydraulic press, you can just use like a vacuum compatible carbon tab and just dip it into the powder of interest. You also may need to do that if you only have a very limited amount of powder. So that's potentially similar to like a SEM-EDS type sample prep that some people may be familiar with. And we can analyze anything that fits within this 83 millimeter by 83 millimeter area. So that could be multiple samples if you're doing a quality control application and verifying the chemistry of multiple batches of things. It could be, one large material like we saw with the 100 millimeter tensile bars. Essentially, they just stuck off the edge a little bit here, and we didn't move the stage to hit the edge of our samples, sample chamber. But yeah, again, a lot of versatility and minimal sample prep required.
Great, thanks for sharing that. And the picture was very valuable for that as well. There was a question that came in about, are there plans to use ICME simulations to optimize and assess your capabilities, either on Exums or with some collaborators?
I don't have a specific project in mind where we're talking about kind of enhancing ICME with experimental data like this, but it certainly seems like we would be well suited to do that. Again, just because of the fact that we can analyze, anything and get the full periodic table, and because we don't have to be, tuning or searching for specific elements with the time of flight, it would allow you to get really, really quick feedback. Again, I mentioned, as little as 15 minutes for just kind of a quick scan to verify the chemical composition. Obviously longer if we're doing a larger elemental map, but I think this technique would be well suited for the experimental pieces needed to validate an ICME workflow. And so we would definitely be open to discussing something like that.
Excellent. This is about, what is the wavelength of a LA laser? Are there any limitations to the laser wavelength?
So our specific laser that we use is a 213 nanometer picosecond laser. So the 213 nanometer we have found is pretty versatile for a variety of materials. Where we do reach limitations is something that is like really transparent. So like a transparent glass. That's typically not an issue in this industry. There are some like geologic materials that can potentially be, too transparent to get a good laser coupling. But we do have experience analyzing, black glasses or things that have some opacity to them. It's just really something super transparent that would be a limitation. And then the other piece of that picosecond, that refers to how fast the laser is. And, I alluded to the fact that we can analyze a matchstick, energetic materials. Essentially what a picosecond laser allows us to do is stay in this cold ablation regime where we're not creating any sort of thermal effects and we're not, igniting an energetic material as we fire our laser at it, and allows us to, not be introducing any sort of material changes as we go through the ablative process. We're literally just removing material, not changing the properties, and then ionizing it to analyze it with the mass spec.
Thank you. Speaking about the ablation, how much material is removed by Massbox ablation process?
Yeah, so it is material dependent, and I mentioned there is some flexibility in terms of the user as well, being able to change the laser power. So we have experience doing like thin film analysis where we're removing on the order of tens of nanometers per material. Then I also alluded to this study where we actually profiled through 360 microns of a carburized steel sample. And in this case, we were trying to get to this very deep depth. And so we chose to increase the laser power and overlap the spots so that we're removing about 3 microns of material per layer, and allows us to again get this very deep depth profile. So, it is material dependent, but there is some flexibility there, and it can range from tens of nanometers on the low end all the way up to single-digit microns on the high end.
Okay, there's a couple questions that have come in specifically of how is the Massbox calibrated, and then what does my facility need if I were to install a Massbox? So that's kind of a twofer question. So if you can break that down for us, Helen.
Absolutely. Yeah, so when it comes to calibration, because we don't have some of the same environmental changes that other techniques have where they're, using gases and plasmas and things that change kind of day by day, we have, less of a kind of a traditional calibration process needed. And what we'll do is we'll run these certified reference materials that I talked a little bit about in the first application example that I went through, where these certified reference materials, we have a lot of confidence in the accuracy of these results. And so we'll run one of those, we'll validate that we're getting the accurate composition for all of the elements of interest within the range of uncertainty, and essentially just verify that we're getting the results that we would expect. So for example, like in our demo lab, we've got 2 nickel 718 reference materials that we'll run every Monday morning. We'll use one to quantify the other, use the other one to quantify it, and essentially just verify, okay, yeah, we're getting the right answer for these reference materials. We're confident that our instrument is behaving as it needs to for accurate quantitative data, and then we proceed with the analysis. So you can either do it that way, or you could always run a certified reference material in your analytical session. Again, I showed you what the sample tray looks like, and so you can always put a known certified reference material like this one in each session and just verify that the results you're getting on that match what you anticipate. So in terms of calibration, yeah, essentially it's just run something that verify that you're getting the results that you would expect. In terms of just kind of like preventative maintenance, we're typically performing preventative maintenance on mass boxes twice a year, just to validate that laser power and everything is still meeting the spec of how it left our facility. And what you need is just a desktop of space. It's about a 2-foot footprint, 2-foot by 2-foot footprint. It's just a typical power outlet, not even 220. You know, it could be 110 volt standard power. And the biggest challenge is just it's very heavy. So you know, you'd want to make sure that that table can withstand the weight of the Massbox. But in terms of size, it's pretty minimal space. All we need is that electric power, and we don't need any additional, you know, fume hoods or argon gas supplies or any of those other kind of ancillary pieces of equipment that other mass spectrometry techniques require. So pretty minimal in terms of setup. Oh, I should also mention temperature control. We do request that we're in a temperature controlled, and by temperature controlled, I just mean room temperature, because what we found is that areas where maybe the air conditioning isn't as good, once the room starts heating up quite a bit, it can impact the laser power and the laser performance. That doesn't mean you can't run with the instrument if your air conditioning goes bad. It just means that you may be getting a little bit lower power. So you would want to make sure that you're doing that, you know, certified reference material in the same session and correcting for any low laser power that you may be getting if the room is kind of out of that room temperature range. So temperature control, standard power, desktop that fits the footprint.
Excellent. One other question, and I think that we're coming to a close on our presentation today, but is there any requirements for periodical maintenance, cleaning, etc.?
Yeah, so you know, the biggest sort of like cleaning required is just to remove any sort of extra neutral particles that may be left over after the ionization process. So occasionally, like the extractor system, which is where this ionization process happens, there can be neutral particles that build up on it, or they could potentially build up on the edges of the sample chamber. We just suggest that you wipe that out and take your extraction system out and swap it with a clean one. We always give our customers 2. So anytime you're changing materials, it's a good practice just to swap out your extraction system, just to verify that you don't have any of those kind of extra neutral particles built up. But yeah, fairly minimal when it comes to maintenance and cleaning. And as I mentioned, you know, we'll come for biannual preventative maintenance visits. The biggest thing there is we've got this sacrificial glass window that will rotate based on the number of laser shots, and that essentially just protects our optics systems. It's a sacrificial glass window, so that's something that needs regular changing. But you know, overall, we've designed this to have as little maintenance as possible and be as easy to maintain and validate that you're getting repeatable results as possible.
Excellent. Well, I think that is a wrap. Ellen, you were very comprehensive with the presentation. Appreciate it. You did get a compliment from the audience saying great presentation, interesting. So very good information. So again, thank you for this insightful and engaging presentation. Obviously, Ellen has put her information up there if you have questions specifically, but we do value and appreciate your membership, Ellen. So thank you. Your work at Exum Instruments, you know, underscores the importance of accelerating advanced materials. So thank you very much. I appreciate it. And thank all of you for joining us today. Mark your calendars for our next Liftoff webinar, which will be December 10th, presented by 3D Chimera, Parts on Demand, ready to run a validated solution. So thanks everybody for joining us. Have a great rest of the week. Bye-bye.
Thank you so much.